All right, thanks everybody for joining today. We have a follow-up talk to a talk that was given about 2 years ago by Jeronimo, and he wanted to give everybody an update on this project and talk a little bit about some of the results. So I'm pleased to announce that Jeronimo is going to be talking a little bit about in-band telemetry and the experiences that AmLight has had after implementing this for about 2 years now. So I'll turn it over to you, Jeronimo.
Thank you, Jason. Good afternoon, everyone. Thank you for those who were able to join. Yes, as Jason mentioned, this is going to be a follow-up to the presentation that was at the end of 2019. It was a year ago, pretty much. Basically, what I want to share is, well, what was that we learned so far? But even for those who did not attend that one, I'm going to give a little bit of a refresh at the beginning, explaining what in-band telemetry means, what our project aimed to do, and also everything that changed since we first defined our goals. So again, my name is Jeronimo. I work at Florida International University. I'm the Chief Network Architect of the AmLight project. So this is going to be our outline. Again, I'm going to start with the in-band network telemetry. I know some people might not be aware of what it is, what the Amlight-INT is, and what we accomplished after 2 years, all the challenges, what we're trying to monitor, what we're monitoring, how we're going to be rolling out this to production, some results, what happens next after this, future challenges and opportunities. And as it happens to most of our presentations, the idea is to be fully transparent, very informal, just to share results, just to share experience. All of this was very new to us at the beginning, but I believe it was an incredible journey. So starting with the in-band network telemetry. So INT is a P4 application that records network telemetry information in the packet, while these packets traverses the path between two endpoints. For those who don't know, P4 is a programming language for a forwarding plane. So that's how you program. It's a way for you to program a ship or a switch. And INT is a use case for that programming language. The main difference of INT compared to other solutions is that with INT, the telemetry is exported directly from the data plan, meaning there's no control plane involved, meaning there's the main CPU of the device is not affected at all. So this is very different from the way how we do SNMP, we do IPFix, NetFlow, SFlow, because all of those technologies that they use the main CPU of the box to export that information. And that's the reason we have some sort of sampling, or we cannot do this in real time because we have to save those resources because that CPU is shared. With INT and P4, the idea that this is going to be done entirely by the data plan, meaning that you can track or monitor or evaluate every single packet at line rate and in real time without affecting any other service in that box. And there is a number of possibilities of information or telemetry that you can get from each device. For example, you can get a timestamp on what the first time that packet was seen. You can have an ingress port, egress port. You can have the buffer utilization or occupancy. You can have a sequence numbers. And INT is very flexible. You can have pretty much whatever makes sense to you. And you can even have INT over wireless devices and have like a wireless signal, for example. And those were the 4 questions that were the main drivers for INT in 2015, 2016. So how did this packet get here? So the idea was to fully understand is the sequence of network devices a packet of visit along the path. Some people call this proof of transit. It has an IETF is also working on that name. And that is that benefits your network because you can have a path tracing that even addresses link aggregation, ECMP, or layer 2 network. It doesn't matter what kind of technology this is done at the layer 0 is done in the hardware. So that packet, that interface is going to be recorded, and then you have the true visibility, the path taking inside the device. Why is this packet here? Well, as you probably remember, before was creating the vibe of SDN, and there was a lot of protocols to do SDN, and there was a lot of ways for you to play with match and actions. And sometimes you want to know, well, what exactly was the match or the actions that were performed in that packet that led the packet to get to where it is right now. So this is also possible with INT. You have information, for example, for how long a packet was delayed inside each box. You probably heard of the concept of buffering, and buffering is something that all the switches must support. And buffering is the main reason why we have jitter, for example, right? So because you have a different end delay because it depends on the utilization of that buffer. So INT helps you to understand how long was the packet buffered per device, and then also gives you the availability to see which device along the path was responsible for jitter. And in the moment that you have jitter or you have delay because of buffer, then INT gives you the flexibility to look at who else was in that buffer with you. So what flows were using the same resources as your packet that led to that delay. So this is very important because sometimes you don't want to just know that there was a delay. Sometimes you just see that there is a delay, but you want to know why there's a delay. And this is how INT could be very instrumental. So how does INT work? Basically, you have two nodes, node A on the left, node B on the right side. Those nodes are just computers. They are not aware of INT at all. And in the moment that they send a packet, a TCP/IP packet with a payload, the first switch that supports INT, and I'll call INT source switch, represents by the number 2, pushes a header and then start adding telemetry. And then every switch in the path that supports telemetry will also add telemetry, its own telemetry, and then starts stacking up telemetry. If the switch in the path doesn't support INT, they just ignore because this is after the TCP/IP headers. And when it gets to the last switch in the INT domain, basically what the switch does is it extracts all the telemetry, creates a report, sends to the telemetry collector, which is step 5 here, and then sends the packet to user, which is step 4, in the same way as the packet was received by the first device. And this happens per direction. In the moment that the B responds to A, then the roles are going to be inverted. The source switch will be number 5, and the sync switch will be number 2, and then there will be another telemetry collector in the other side of the network. Just a little bit of context about AmLight. AmLight is a distributed exchange point, is an NSF, a National Science Foundation project, part of the RNC program. It basically, the main mission is to connect Latin America and Africa to the US. It has a bunch of 100 gig links. But the main thing about this is this infrastructure is being in place for a number of years, almost 20 years. No, maybe 17, yeah. But the main thing is that since 2014, this is a production SDN infrastructure. It was always production, but since 2014 is SDN. Meaning that we deployed OpenFlow 1.0 at the beginning, then we started OpenFlow 1.3. We always did NSI for inter-domain provisioning, and we have been playing with SDN concept for a while. And this is a production that carries commercial and academic traffic, and it has been working very nicely. We have multiple points of presence in Florida, Brazil, Chile, Puerto Rico, Panama, South Africa. And the main driver for INT, it was the SLA, or the service level agreement of one specific AmLight member, which is the Vera Rubin Observatory, aka LSST, or Large Synoptic Survey Telescope. Because the LSST or Vera Rubin had a very strict SLA, that's the reason we decided, well, we need more instrumentation to be able to respond to that SLA. And that's what led us here. So what happened after we realized that we needed more instrumentation was we created this Amlight-INT project that is a sub-award of the Amlight project that was awarded in 2018, at the end of 2018, and it had those goals. First was develop and deploy INT-capable switches. At that point, there was no production device that you could purchase that had INT. So there were white boxes that supported P4 runtime, some OpenFlow, some, but none of them were doing INT. So we needed to close this gap. We need to find a vendor that was willing to change its code to support INT. And then we wanted to purchase INT that was capable of addressing our needs, not just in terms of INT, but then we had to keep maintaining the SDN and the number of 100 gig ports and all of that. And we also had to deploy or develop a software to collect that telemetry. So that's what we call the INT telemetry collector, or just telemetry collector, or INT collector, that basically receives the data from the switch and processes that metadata. And then we wanted to develop a methodology to collect and export this data in real time to feed our SDN controllers and users with monitoring information. One thing that I forgot to mention, that was that LSST also wanted to have real-time visibility of the network. So they eventually asked us for, can I gather data from your routers every 1 second using SNMP? And then we say, no, you cannot. And then we had to find an approach because they still needed information. So the idea was, at the end, we wanted to create this network telemetry design pattern that could be used by AmLight, but also by other research and education networks. So this figure here on the side shows a little bit of a simplification of what we're talking about. We have those blue boxes. Those are the P4 switches. And you can see we have them in multiple locations. And in some locations, we have those gray boxes that are the telemetry collectors. Those are just computers that receive data and do processing. Those receive massive amount of metadata and then simplify, create those network status in pink that are just like summaries. And those summaries go to a central location, which we call SDN looking glass. And the looking glass exports that information to users that want to consume that information. So this project is a collaboration between FIU and Noviflow, with aiming to do this expansion. Noviflow is a Canadian company with some presence in the US. They do software development for networking, and they have this NoviWare operational system. That was the software that we wanted to use before INT, because they have a great support for OpenFlow 1.4. And also they have support for bidirectional forwarding detection, link aggregation, and a path towards P4 runtime. So Noviflow was responsible for expanding its own software, NoviWare, addressing the FIU requirements, and then FIU was responsible to collect, to develop the other side to collect that information and evaluate the Noviflow switch. And then we decided to use, at the end, this switch. This was a solution that Noviflow presented to us. It's called WB5132. It's basically a barefoot to finish chip. So it means that it's very programmable with a P4. They have a support for P4 runtime, but this is a new thing. They always had a very good support for OpenFlow 1.3, 1.4, BFD and lag. Those are the things we had in mind. And they have 3200 gig interfaces with a kiosk FP28, meaning that is a one rack unit solution that is very easy to maintain and very scalable. And now we're using INT at the version 1.0. By the time that we started this, that was the latest version. But today there's a 2.0, but we haven't like gone that direction yet. So we're still working with 1.0. So for those who attended the first presentation, 2019, those were the research challenges that we wanted to address, and now those are addressed. So in red is the new content, in black is the questions that we had at that time. So one of the first one was, well, how many flows can we monitor using the INT collector that we developed? And we realized that after a lot of challenges, and I'm going to explain those challenges, now we are able to capture for the whole AmLight 10 million packets per second, if we don't need to do like extra workarounds and just using the nodes that we have. And you're going to see if this number is good or not later, but I left the air quotes for processing here because that's very personal, what we do with that data, and I'm going to show you later. What is the impact caused by INT? Well, First, if you're adding telemetry, means that you're changing the packet, that you're making the packet bigger, means that you're going to introduce some delay, means that you're going to increase the MTU. So those are the first things that we had to address. Luckily for us, the delay is not perceptible, 450 nanoseconds. Our network is a long haul network. Each link has at least 50 milliseconds, which is almost 10,000 times bigger than this. The MTU that each switch, no, in regards to the MTU, each switch add telemetry equivalent to 24 bytes. So depending on the number of switches that you have in the path between two endpoints, you can have a lot of telemetry. But luckily, the Tofino chips has MTU of 10,000 bytes. So we have plenty of space for MTU. It's not our goal to fill the whole 1,000 bytes, but at least we can have 10, 9, 11 for sure. The only concern that you need to have is legacy device. So if you have one legacy device that the MTU is just like 90 to 100, then you have to be aware that you only have space like 196 bytes for telemetry. So you have to address this. It's up to your orchestrator to decide when to add telemetry or not. Collocation, well, if you have a collector connected to a switch to gather the telemetry, you need space, you need collocation, you need power, and those machines are not small machines. They have to be very powerful. So this is extra collocation. In some places, we are very restricted. So we have to be careful with the size of the machines, where to place and how many of them to place and per pop. So this is an issue, as an impact that we have to address. How to dynamically enable INT. This is, at the beginning we thought, well, if this is deployed with before in time and in Tofino, that's going to apply to all the flows. But luckily, we came up with a very nice, NoviFlow came up with a very nice solution that was, well, we're using OpenFlow for everything. So why not just using the experimental actions, which is reserved for this kind of functionality, and expand the OpenFlow library, and then just add the actions that we need. So that means that we can leverage the same matches that we had yesterday, and tomorrow now we just need to add more actions, and that's it, and the network is ready. So it's very simple, it's very scalable, allows us to do very granular measurement. We don't need to measure Netflix performance. We just need to measure LSST, scientific instruments, LHC, and then leave Facebook and Netflix alone. What is the definition of real time? Well, if you're from computer science, the real time domain, you're probably going to hate us. Well, usually we got very bad feedback. People don't like we use real time word, but in fact, it is a free country, so we're going to say that we create our own definition of real time. And real time for AmLight means that we want to receive an instruction of consolidated telemetry report under 200 milliseconds. Meaning that we need to collect telemetry data, process, send summary to the central location, process summaries from multiple locations, cross the data, generate an alert. All of this under 200 milliseconds. It's plenty of time. We can narrow down this to 100 milliseconds, but we're very comfortable. And we're going to get to a point that there's a limit, because Brazil and Chile are 55 milliseconds away in propagation delay from Miami, which is the central location. So we still have to wait 55 milliseconds for that telemetry to get to the point in Miami where it can be processed and the SDN controller can do something with that information. How to store and process multiple gigabits of telemetry? Well, this is the main challenge. Process, we found a solution after some time. I'm going to talk about this as a challenge one. Is store? No, it's not going to be that easy. We haven't found a solution, and I'm going to talk more why about in a couple of slides. But what we had to do is we had our management plan per site, where each POP had its management plan for SNMP, NetFlow, or SFlow that we use, or SSH. But then we had to create a high-speed management plan where you have multiple 10 or 100 gigabit links, just to create this overhead to receive all the telemetry in just one node. We don't want to have one collector per switch. We want to have a collector per site. So you need to gather data from all the switches into this single collector per site. And how to share this? It's a lot of data. Well, right now, the only thing that we have is summaries and events. Those are stored in a time series database. We use Grafana for visualization. We are in the prospect of developing a gRPC for those users that want to consume this in real time, but we haven't received any hard requests for that. So it's kind of on hold right now. So what is the metadata that we have access, and how are you using that metadata? So basically, each switch provides us with a switch ID, ingress port ID, egress port ID, ingress timestamp, egress timestamp, egress queue ID, and egress queue occupancy. And each report that includes the telemetry from all the switches also includes a timestamp and also sequence number. That's how you keep track of you lost something. And obviously, the original TCP IP headers. That's how you correlate, for example, with a VLAN or a pseudo wire. You need the original header, but we have no payload. So the first application that we wanted, and it was the easiest one, is like proof of transit. It's basically record the path taken. We use the list of switches, and each switch we use the switch ID, ingress port, and egress queue ID. So with this, we are able to trace every packet and recording those changes. So if we go through one port member in the lag, and then we go to another port member in the same lag, we're going to record that we're flapping, there's a hash error or a mismatch that is leading to some instability. So we're not using always the same path. And also, when you have those links that flap a lot, and sometimes you have links that flap like 1,000 times in 1 second, so it takes longer for you to detect that through syslog than it would be with INT. So this is the kind of thing that benefits us. And one of the things that most of the solutions, or none of the solutions out there that I know of have, is you have a trace route that also tells you what was the buffer that was used, which queue of each interface was used. And this is great for you to evaluate QoS policies, because usually you have to do this like using a CLI and keep looking at counters and sometimes isolate that queue to make sure that that's the right one. So with INT, you just know, oh, this is a queue 0, 1, 2, 3, all the way to 7. So it's easy for you to track. You have instantaneous ingress and egress interface utilization because you know the ports, you know the packet length. So then you can just put those two together and then get the interface utilization. The way we're doing today, we're collecting this information and reporting the egress outgoing interface utilization every 50 milliseconds. That's just a number that it's pretty good for us. We can tune it down if we need it, but we're probably going to need more CPU if we decide to be more accurate than that. So for now, instead of having SNMP data showing link utilization every second, then we have every 50 milliseconds. So it's 20 times better than we used to have before. And because you also have the egress queue ID, you can also create the bandwidth per queue. We don't do this because we basically only use 2 queues today, but it is the kind of thing that you have the flexibility to do. Instantaneous egress interface queue utilization, that's what I mentioned before, but not bandwidth. In this sense, the memory. So you can monitor the buffer utilization per packet. So meaning that when the packet lands in the buffer, the packet records how much of that buffer was already in use when the packet landed there, including itself. So this is great because then, again, you can monitor every queue of every interface of every switch. And then you can use that to evaluate the QoS policy or even detecting the source of packet drops. Because if you start seeing that there is a queue that is always close to 80%, that's when the schedulers start dropping packets. And dropping packet is the kind of thing that you don't want, because it's the kind of thing that you can have some sort of control. So if you have visibility that the buffer is getting close to a limit, or then you can trigger on an alarm, or you can trigger a reaction, you can trigger like a traffic engineering policy, and then load balancing your traffic. So this is great. Sources of jitter, of course, because if every packet has in it with the metadata the time that was spent per device along the path, then you know which device was the one that really introduced delay or it created the jitter. There is the variation of that delay. So this is great when you have like real-time applications or when you start seeing that there's an interface, there's high utilization because you have a fan out, you have a lot of sources coming out through just one link, and then maybe it's time for you to improve your traffic engineering policies and QoS policies. So this is great. And this is specific, especially useful when you want to track microbursts, right? So if you start seeing that not necessarily have a lot of bandwidth, but you start seeing that there's a lot of packets and a lot of DDoS coming and then creating a burst, and then you're going to see a lot of buffer, and you see that the buffer increases like suddenly and then goes back to normal when the microburst is over. So is a way for you to detect this sort of events. So this is the first challenge. Let's talk about now the implementation. Just to give you some numbers, 100 gigabit flow with a 9,000 bytes packet generates around 1.5 billion packets per second. At AmLight, we have 4 to 8 switches connecting Chile to the US. Each telemetry can have up to 300 bytes. That's when we cap on purpose. So it can have all the way to 300 bytes, depending on the number of switches. If you only cross one switch, it's going to be 36 bytes plus headers. Each packet, each user packet triggers a telemetry report, meaning that if there was 1.5 million packets per second, there will be 1.5 billion telemetry packets per second. And which, when you do the math, it leads to something like a 4.5 gigabits per second telemetry report for every 100 gigabit flow, which is 4.5%. It's a lot of traffic. It's a lot of information. And the worst case scenario, when you have a single switch exporting all the telemetry flow, means that that switch only has one source. That report has only one source, one destination, meaning that you cannot hash that on your NIC, on the Linux box, to do like use multiple queues and multiple cores. All of that end up going to just one core on your machine. And the solution that we end up deploying was using something very new called Express Data Path. It's part of the eBPF library. And let me give you a little bit of details about that. So for those who know what DPDK is, XDP is something very comparable. It's a lot simpler, and the idea is to do the same thing. You have a thin layer at the lowest part of the network stack for those incoming packets. It's not like bypass of the Linux kernel. Now, you're in the front of the Linux kernel, or the first step of the Linux kernel networking stack to do something with that packet. And you can just deploy a hook to that. That could be in the kernel itself or on the receiving ring of a NIC, if the NIC supports that. And then you can even like outsource that processing to a NIC. So meaning that you have a lot of power to receive telemetry reports because you don't have to do the socket buffering allocation and also the context switching that the Linux kernel has to do it. And it does by default every time the packet just goes to the TCP/IP stack. So if you are one step behind before the TCP/IP stack, that means, well, I can do some parsing of that packet and decide if I want to forward up to the stack or I just want to end it here. So you can drop, you can redirect, you can do some sort of calculation, and then you decide what you do. In our case, what we do is once we receive, we parse, we drop it because we don't want the socket buffering allocation happening because that's where it kills the machine. So in the end, we operate in the XDP layer, and then from the XDP, we have some libraries. Well, not us, the community has some libraries to export that to InfluxDB. So then we export that information to the time series database, And that's how we have the information that we have today. Uh, So the main use case, the most famous use case for X2P in the community is Cloudflare with the DDoS mitigation service. They demonstrated this multiple times that it can handle 20 million packets per second per node. So that's a massive number for just one Linux box. And just to give you some comparison, before when we're using user space with Python 3 or C, we're seeing drops around like 5,000 packets per second. And with XDP, we're doing per core 3 million packets per second. So this shows well the huge potential that XDP has, but I'm not the expert. I promise I will submit a presentation to the Lunch and Learn in the future to talk about XDP because it's an amazing and simple tool for some of the development that we need to do once in a while. So the second challenge is, well, we wanted to store that telemetry, but we realized it's not feasible. So what we decided to do is, so in the XDP code, the processing that we do, it's not storing or processing every single telemetry report and save that. What we do is, well, look for events. We want to see changes of behavior. So if there is a queue in one device that increases or decreases more than 20 kilobytes, we record that. If a path changed, we record that. If a hop delay increased more than 2 microseconds, we log that. If there's a total delay end-to-end increase more than 50 microseconds, then we log that. And if the interface is using more than 80 gigabits per second for more than 50 milliseconds, then we log that. So basically, is this graph shows we have those little green boxes, and those green boxes are events, right? Those are telemetry reports. And we have the lower bound and the upper bound. And for the first packet, we log it. And then the fifth one, it's above the upper bound, then we log. And then everything that is in between the new upper and lower bound, we kind of ignore until we get an event that is outside of those boundaries. So this saves us a lot of not just disk, but processing, because sending to InfluxDB means sending to the user space. And we only want to send to the user space when it's absolutely necessary. So the point is, the more granular metric that you want, more CPU you're going to use, because more context switching you're going to be performing. And then what resulted for us is, yeah, we have a close to real-time processing. It's very good. We don't drop a lot of packets. We usually drop 1 or 2 or sometimes 6 packets per second of telemetry. But we lose a lot of the granular measurements. So if you were a machine learning kind of researcher and you wanted to see every single telemetry report, well, I have bad news for you. You have to get used to some information, which leads to the challenge number 3. We participated of a few meetings with machine learning and artificial intelligence researchers, and they keep complaining all the time, oh, they have no grounding truth for learning algorithms in the networking field. They don't know what exactly is a DDoS. They don't have a reliable data store or database that they can use and say, oh, this is what a DOS means. I mean, like public. Of course, you can generate your own data source, but they lack this. And to have this, they need reliable and complete data sources for this to create the grounding truth. And that's the reason we wanted to do it. But let's look at the Vera Rubin telescope. Vera Rubin is going to send data every 5 seconds, 13.6 gigabytes of data every 5 seconds. At the end, each 5 seconds is going to generate 337 megabytes of telemetry. During the night, the telescope is going to do this 1,334 times, meaning that at the end of the night, we're going to have 450 gigabytes of telemetry. That's not images of the space. That's just telemetry. So this is just one night. This is just one flaw. And you can see that this is going to grow a lot. And then you have to ask yourself, well, should I do it? And how do I do this without increasing the OPEX? Am I going to need more rack space, more power, more air conditioning, more infrastructure to just to collect this? And if so, how long, where, how am I going to store this? Should I store with all the information or just remove some of the telemetry data? Maybe I don't need every single thing that is in there. And how do I do this? How do I share this kind of data, preserving privacy, but not compromising research? And what else do I have to provide? Do I have to provide the topology? So again, there's a privacy requirement that we have to address. So this challenge, it's wide open. We're looking for collaborations. If you have a suggestion, let us know. This is not part of the scope of the project. This is part of the ideas that we wanted to support research, but we kind of struggle with that. So let me share some results and some products. The first one, well, INT is a protocol, is a standardized protocol. So it's only natural that you start with a dissector for Wireshark. So this is the dissector created by Noviflow that shows you on the left and in the center, the headers. And on the right side, you see the stack. You see two switches, one switch with the ID 33 and the other switch with ID 35. And that's the information that I was talking about before. The second product was the collector. So we created two versions. We started with the Python edition that we use for evaluation, for validation of the switch, for to play with the test bed, and to learn about INT and the possibilities. So it is a good tool if you have less requirement than less than 5,000 telemetry packets per second, because if you have less, then you have high visibility. You can store every single telemetry report. It's easy to use. You can just create an application that connects to RapidMQ, and that's it. And then you do whatever you want with that. But if once you decide to move this into a little bit more hardcore environment, then you have to go towards the XTP edition, which is the XTP is basically a limited C code, which makes it very hard to upgrade it to an expand. It's a very limited scope because it's almost like a device drive inside the device drive. But from the other side, then you have a lot of scalability. You have a lot of flexibility in terms of the functions that you can do with your C code, but you have to be aware that if you start with the idea of saving everything or sending everything to the user space, then you're gonna kind of struggle. There are multiple ways of doing this, and an amazing approach was Richard from ESNet presented that he did with DPDK. He sends back to the network and do some parsing, and then he used some hash to receive that information again. You can do it. This is part of the roadmap for us to try, but at this point, we're not planning to do this right away. So just let me show you some screens with the information that we have. This is the lab, just to give some idea. Obviously, Amlight is not like this, but you have those two nodes on top and two nodes on the bottom, and then you have 5 switches in line, and the flows go from the right side to the left side. So on the top, you have machines generating from 10 to 50 gigabits per second, sometimes a little bit more, and on the bottom, the same thing. This could be TCP or could be UDP, okay? So let's prove to you that this is in the switch, right? So this is an open flow thing. So you can see here, this is an output of an open flow entry on the switch, and then you see the actions. The action is an experimental action, and on the left side, you have the push in, which creates space for the header. And then you have add INT metadata on the right side, which adds the telemetry information. You see that you don't get to choose what information the switch will send as an open flow action. You do this on the telemetry header. So on the header, the first switch tells what kind of information that switch supports. And then from now on, all the switches and the topology have to follow the same approach. This is just an example. You can see here, for example, the jitter, the Q0 along the network. Each column here, you have two colors, orange and gray. Each one represents a different switch. And then you see the jitter that was created by that switch. This is just the beginning of an IPERF communication. And the blue line going up and down is the packet size. So, you know, In one direction, you send a big packet to test performance. The other one, you receive feedback. So nothing too fancy, but just give you the idea that you can see every single packet. Here, the same thing, but now we're monitoring the queue occupancy of a beginning of an iPerf data transfer. So you see at the beginning on the left side, and the timestamp here is in nanoseconds. Yeah, there's a lot of negotiation that takes place, and then you start seeing the test itself. So this one is a TCP 60 gigabits per second flow between one source and one destination. You can see that because this is using a 9,000 bytes packet, all the switches in the path, they have here the first column with the name of the switch, the second column, the number of the interface, and the third column, which is the queue that was used for that packet. And then you have 115 cells. Each cell represents 80 bytes under the finiship, which leads to the packet size, which I don't remember if it's a 1500 or if it's a 9,000. Yeah, 9,000. So this is a 9,000 packet. And because it's one source, one destination, of course, there's always going to be base 115 because that's one packet. There's no multiple incomings and one outgoing in this case. And on the bottom, you can see here that instead of showing the number of cells, I'm showing the hop delay, how long it took inside that device to do this sort of forwarding. And then you can see the variates. This is a nanosecond, is very small, but you can clearly see that the first hop, the hop on the bottom, has at least the double of the following ones, which it means that this is the guy that is adding the header, is making space on the IP packet and the user packet to accommodate the INT needs. So it's natural that spent a little more time on that. Here on the bottom, you have an example of a base situation where you have multiple sources going out through the same link, which in this case was no v3, port 4, Q0. There is a lot of traffic because there's multiple 100 gig flows coming in, 100 gig port to come out, then there will be buffering. And then you can clearly see that now the hop delay for that node is at least five times higher than before, because now I have to do buffering. Now I have more packets to manage, and then I have to use the memory. So this is what this tool, the QTOP, is telling on that. So this is now visualizing the same thing through Grafana, and then you can see the queue occupancy of all the switches, all the interfaces, and all the queues that we're seeing so far. And you can clearly see that it keeps varying between a few bytes and all the way to 20 kilobytes. And 20 kilobytes in this case is basically, well, 2 packets on the buffer, right? Because 2 sources sending packets to that same destination. So it means that that egress queue has some packets on it. And this is not an interface that is using more than 80%. So there's no crazy buffering here happening. It's just 2 packets, and then they go, the 2 packets that they go, the 2 packets that they go. But you can clearly see the time scale here, that the number of variations here explores the maximum or the minimum refresh time of Grafana, which is 200 milliseconds. So every 200 milliseconds, Grafana updates and shows these ups and downs. And all of this here is a couple minutes, 5 minutes maybe. And then you can clearly see the number of measurements or the number of events that led to a change that we recorded. Here is just for hop delay. Same thing, you see that, well, if there's only the switch that has buffering, that will have variations, right? Because the others have no buffer. It's just one packet come in, one packet come out. So the first one, which is the blue line, shows the variation going from 1 nanosecond or 1 microsecond, almost close to 47 microseconds. And this is because of the buffering. You have to add those to memory, and then you have to process this. So you see here in the same time interval of 4 minutes, less than 4 minutes, the number of times that there was a delay variation, there was jitter. And that's, in some of the cases, not these small, but in some of the cases, you can actually see when you ping those numbers reflected in the ping, because the ping shares the same port. And then you're going to see the ping varying and matching those numbers that you see here on the screen. So remember when you used to think, oh, why the ping shows 1 millisecond, now 2 milliseconds, then 1 millisecond, then 10 milliseconds? Well, the answer is on the screen. You can clearly see which switch is making that happen. Here it's a little bit more elaborating. It's just us playing a little bit last year. We had that same picture, a flow on the top, a flow on the bottom, and then we had a TCP flow for those. TCP on the top to TCP on the bottom. And TCP is very friendly, and you can clearly see here on the left side of the red bars that TCP was coming to an agreement, and then everything was fine. There was a little bit of variation. Then they start hating each other, and then we switched to UDP. And then you can clearly see that they don't like each other, and then they try to use all the resources, and they consume all the resources. And then you see that the queue is always full. It's not variating anymore. You can see the delay is constant, always at the maximum of 150 microseconds. But it's interesting to see this. And what we want to do right now is to start simulating more events like, oh, let's simulate a microburst, let's simulate a congestion, let's simulate a mix of TCP with UDP and see how these displays on the screen. So then we train our eyes to identify behaviors, problems, and then we get to a point that we can teach a machine to automate this sort of processing. So this is what we're doing right now. We're doing a lot of these simulations to learn the behavior from the switch perspective for each one of those scenarios. Well, this I talked before is how we're doing this. Each site has a management plan with a management network, a high performance management network, and all the data lands on the collector processes in central location. No news here. And conclusions. Well, monitoring every and any packet is possible with INT in-band network telemetry. It has increased the network visibility beyond our expectations. We knew it would be great, but we didn't know it would be this great. Combining INT and legacy monitoring tools will enable us to track any performance issue and user complaint, especially those SLA driven. So once the LSST becomes production, we want to be ready to answer their comments and questions about poor performance issues, for example. So we want to do like a combined INT with learning tools to create reliable trends and move towards a closed loop orchestration, which is a part of the answer to the next question. What happens next? So basically, we want to maximize the fact that we have an INT substrate, right? It's a lot of data. When we created the product, the idea was to, well, we want to have INT. So now we have INT and we want to do something. And through time, we identified multiple opportunities for us to explore that massive amount of data that we have. And currently we have those three awards from NSF. One is a CC store called Q Factor. It's between FIU ESNet. That we aim to expand the management plan or these INT domain to the DTNs. So we want the DTNs to receive the telemetry data and have better visibility of the network. The AmLight product was awarded for another 5 years. So for the next 5 years, we want to develop like learning systems to consume telemetry and policies and create a closed loop orchestration. And the Atlantic Wave STX, which is an inter-domain thing, will benefit from INT and other telemetry solutions for consolidate different telemetry in different format from different domains, understand how privacy will be addressed, and how do we use multiple sources and multiple formats of telemetry to support inter-domain provisioning and visibility. Quick about Q Factor, I just want to show this picture here that is basically the same picture from the beginning, but now the computers, the end nodes, will have the telemetry. By having telemetry, those nodes, they know what to expect the network, right? Remember the TCP congestion algorithm. This was talked a couple of weeks ago. There's three possibilities for congestion control, like based on buffer, based on delay, or a hybrid. And all of those, what they do is they guess. right? They have to guess, they keep testing, they keep generating packets to a point that exhausts the resources and then they come to a conclusion. But what if instead of guessing, the DTNs just ask the switch at real time at line rate? So the switches will provide that information with no impact. The DTN will know exactly how much or what kind of resources are available, and they don't need to guess. If they see that the network only supports 20% of the capacity, don't try to use more than 19. Why try leading to packet drop? You can always stop and pace yourself before you have a drop, because drop is a bad thing. So this is what we're working right now with the ESNet. And ESNet has a telemetry environment. We have our telemetry environment. And the idea is, well, let's prove that there's a benefit in extending the management plane to the nodes. And there will be a presentation down the road about this, because Q-Factor is pretty much like the beginning. The Amlight EXP that I mentioned before, this is just the closed loop that of using telemetry to manage the network and then export the telemetry to validate the network. And we even have a roadmap of how self-optimizing is going to happen. Basically, we want by year 2 to have network reaction or self-optimization under 5 seconds, all the way to year 5 under 500 milliseconds. And all of this is going to be based on learning. So throughout learning of machine learning systems and ourselves and the switch, then we keep optimizing to trust the system to react faster without requiring a validation. So none of this would be possible without this great team. We have PIs, we have software developers, Arturo, Italo, we have David, which is our RU student, that they have been working pretty hard on this. We have an amazing relationship with Noviflow, Arun, Brian, Daryl. And for those projects, we have positions available. Please, this is the part that I beg you guys. We have been struggling to recruit. I'm assuming that you all are going through this. Please, if you know someone that is looking for an opportunity, go careers.amlight.net. We have a senior network engineer, or we have a network engineer, 3 software developers, senior software developers, and 1 postgrad that is going to be based at ESNet. With that, I thank you. I'm open to questions. Please give me what you got, and I will keep this here so you can write down the URL because you need to help us. Thank you.
Well, thank you, Jeronimo. We don't have any questions right now in the chat room. As I say that, Joe was able to type one in, so I'll repeat that. Joe wants to know, how do you envision sharing the data with the research and community tools, direct queries of the InfluxDB, some sort of API through which authenticated requests might happen, or work with groups on a one-by-one basis?
So telemetry data is just a lot of counters. Thank you, Joe, for the question. Telemetry is just a number of counters. For a lot of these instantaneous information like queue utilization, you don't need, there's no privacy issue, because I am only going to tell you switch 1, port 1, buffer 1 has 50, right? So this is not going to help you identify anything or anyone. In this case means that the telemetry, the INT information can be shared to whoever wants that information. And we're looking for people interested in consuming that information. We have never created like a procedure or a policy or focus on that. We're pretty open. Again, because there's no privacy related information in there, you can just have a copy. We can dump the database and you can play with it. But to make sense of that information, you're going to need a topology. The topology, it is something that we can share. We are working with the GreenML community, which is part of the GNA, to have a format for exporting topology that anyone can consume. But right now would be more like a request base. If you need that, I'll provide you. That's it.
Great, thank you for clarifying that. If anybody else has other questions that they would like to ask, please use the chat room. We'll also make sure that we post these slides so that people have access to this information that's being displayed right now. I think you said it in your talk, but when is the LSST data trials going to start? Basically, when is your deadline to sort of have all this in place and need to start using this in production?
Our goal, we have a roadmap by the end of March to have some switches in place. There was a lot of delay because of COVID and like lack of access to some of the data centers in Chile to do major reorganization of the space to install the collectors and also to ship and have someone installing the new switches. Our goal is to, by the end of March, to have some switches in a very passive way, just tracking the traffic that is crossing the switch. And at the end of this year, to have some switches in production in the shape of an overlay. And by mid of next year, to have the network basically fully migrated to this approach. So we're going to be rolling out this in the next year and a half. LSST or Vera Ruby will start production 2023. And I don't know if it's the beginning at the end, but fiscal year 2023 for them, which is after October 2022. So we have time, but we are in a very, we consider the solution is very reliable, ready to go. It's more a matter of, well, how do we get to those locations, see if we cannot travel to go there and install. And I'm the one, for example, my visa does not allow me to leave the country. So I cannot go to Chile to install anything. So it's about it's just like bad timing, but we're gonna do it. Yeah.
Okay. And it looks like we don't have any other questions, so I'll thank you again, Geronimo, for you and the rest of the FIU and AMPATH team for this talk. I think it's really great progress, and this is going to be a great piece of technology to help support that science when it comes online. So we'll make sure that we get this posted, and we're not going to have a talk next week or the week after, but we'll pick up again in mid-February, and I'll make sure that I send around an announcement on the usual lists for that. So thanks everybody for joining today, and hope everybody has a good weekend.
Thank you all. Thank you, Jason, for the opportunity. Bye. Stay safe.